Hi everyone, I am Zehra. My subject is Qubits and Quantum Gates, Foundations of Quantum Computation. Quantum computers represent a revolutionary technology that goes beyond classical computers in processing power. The fundamental units of these powerful systems, called qubits, leverage core principles of quantum mechanics, such as superposition and entanglement, to perform complex and faster computations. Quantum gates are the essential building blocks that manipulate qubit state and enable quantum algorithms. In this presentation, I will explain the nature of qubits, the concept of superposition and entanglement, and how the most common quantum gates operate. A single qubit can be represented as a unit vector within a two-dimensional complex vector space. The state of a qubit is described by a linear combination of the basis states denoted as 0 and 1, which are the computational basis states. A qubit state denoted cat PC can be written like that. Alpha 1 and alpha 2 are complex coefficients that define the state of a qubit and represent the probability amplitudes of the qubits being in the basis states 0 and 1. And qubit can commonly visualize using the block-sphere model. The block-sphere is a mathematical tool used to show all the possible states of a single qubit. It looks like a 3D sphere, and each qubit state is represented by a point on the surface of the sphere. The north and south pole of the sphere usually represent the two basic states, 0 and 1, just like in the classical bit. But the qubit can be anywhere on the sphere surface, meaning it can be a mixture of 0 and 1 at the same time. If alpha equals beta and both are 1 divided by the square root of the 2 like that, it means the qubit is an equal superposition of both 0 and 1 states. This means that when the qubit is measured, it has a 50% chance of being found in state 0 and a 50% chance of being found in state 1. To understand the idea of superposition in everyday terms, we can use the example of a spinning coin. When a coin is tossed in the air, it is neither heads nor tails exactly, but rather a mixture of both. Similarly, a qubit exists as a combination of 0 and 1 states until it is measured. When a measurement is made, the superposition collapses and the qubit appears as either 0 or 1. The probability of each outcome is given by the square of the absolute value of alpha or beta. Thanks to superposition, quantum computers can perform many calculations at the same time, unlike classical computers, which enable them to solve complex problems much faster. Entanglement is a unique quantum phenomenon where the states of qubits become linked, such that measuring one qubit instantly determines the state of the other, no matter how far apart they are. This instantaneous connection allows quantum computers to perform faster computations, enable secure communication in quantum networks, and performs the basis for advanced technology like quantum teleportation. Quantum gates serve as a fundamental components of quantum circuits, similar to how classical logic gates function in classical computing. The representation of quantum gates involves their mathematical characterization. For example, X gate, it flips the state of a qubit, turning 0 into 1 and 1 into 0, just like NOT gate. Hadamard, I mean Hashgate, it puts a qubit into superposition, creating an equal mix of 0 and 1 states. C-NOT gate, controlled NOT, it acts on two qubits. If the control qubit is 1, it flips the target qubit state. And if the control qubit is 0, it does nothing. Represent this is a little different way, as shown. X indicate the control qubit and Y input qubit. As you see on the upper line, the qubit X goes through without any change, but on the lower line, the qubit Y is XORed with the condition bit X. The XOR mentioned here is XOR operation, classical bit operation. As a result, quantum computing harnesses the unique properties of qubits. Superposition and entanglement, along with quantum gates, enable competition far beyond the reach of classical computers, paving the way for transformative technologies of the future. Thank you for listening.